Yes. Yeah, we'll start at 6:05. Let others also. Yes, you are audible. Can you hear me? Okay. So we will start in just 2 minutes. Okay. Can you see my screen? Okay. Okay. So we'll start from the week 2 lecture videos. So these are the questions based on those week 2 lecture videos. So we'll discuss the first question. So have you gone through the video lectures? Hello. Can you hear me properly? Okay, so I was asking that have you gone through the week 2 lectures? Okay. So these questions are based on the week 2 lectures only. So we will discuss and I will explain them one by one. Okay. And we'll discuss some assignment questions also. Okay. So first question is what is you have you gone through week 1 lecture? So do you know little about the aluminum matrix and the introduction? Okay. So first question is about the what is the TPRE mechanism and how does it contribute to the growth of silicon in aluminum silicon alloys? So in aluminum silicon alloys, we have two phases. First is alpha aluminum and uh, eutectic silicon. So this alpha aluminum is the matrix, and eutectic silicon form as a particles and distribute among the aluminum matrix grain boundaries. So the morphology of this eutectic silicon defines the mechanical properties. Means if it is in flake shape. My camera is not working. So if it is in flak or needle shape, so this will be detrimental to the mechanical properties like strength and ductility will be less because the stress concentration generated the needle and flake edges. So how can we modify the morphology of this eutectic silicon particle is the TPRE mechanism. So TPRE mechanism is the growth of these flake and needle shaped silicon particles. So TPRE means twin plane retrient edge. Twin plane retrient edge mechanism in which two silicon tetrahedra join and form a prismatic uh, crystal. Okay, so this at the plane where these two tetrahedra join is the 111 plane, which is the favorable plane for this twin plane for these silicon particles. So, uh, two tetrahedra joined to form the silicon nuclei, and the growth of this silicon nuclei happen along 112 direction. Okay, so this 112 direction, the silicon atoms attach and create flake or needle shape particles. So, so in yeah, so this is the TPR mechanism. First is the twin plane reentrant edge. So twin plane is the 111 plane where two tetrahedra join. So that the base of the tetrahedra is 111 plane. Okay, and and in the one after that in the 112 direction, or I will form a diagram. Yes. So this is a two tetrahedra joints, and this plane is the 111 plane, and this direction is 112. So silicon atom attach at these side surfaces and leads to the growth of this needle shape silicon particles. So this is the solution answer for the first question. It's clear. Okay. Then the second question is, how does the impurity-induced twinning mechanism work to modify the morphology of silicon from flaky to fibrous? So now this flake shape we don't need for the good mechanical properties. So we use some type of modifiers to inhibit the growth in 112 direction. So we use sodium, barium and strontium addition in the this aluminum silicon alloy. So these atoms sits at this faces. So as they sit in at this place, they changes the arrangement of the silicon particles, arrangement of silicon atoms, and induce more twinning by attaching on 112 direction plane. Okay. So as these sodium, barium, and strontium atom attached to this 112 plane, uh, the arrangement of silicon atoms changes and create more twinning planes. So silicon will start to add on the different planes other than 112. So these atoms create isotropic growth. First, the 112 direction was the favorable direction for attachment of silicon particles. But now, as the sodium, barium, and strontium atom attached to this surface, so silicon atom will find another plane to sit, and uh, that will lead to isotropic growth of the silicon crystals. So the needle shape was because of this favorable orientation of these silicon particles. But now the isotropic growth will create a spherical morphology of the silicon particle. So that spherical morphology will not create any stress concentration in the aluminum matrix and will maintain the strength and ductility of that if we make any component from it. So isotropic growth lead to uh, change in morphology of silicon particles. Okay, so we'll move to the third question. Why does higher cooling rate lead to the modification of silicon structures in aluminum silicon alloys? So there is one more method to to avoid this needle shape morphology. So this is the higher cooling rate. So higher cooling rate, first we have to make attention on the this thermal expansion, sorry, solidification temperature of this aluminum and silicon. So if uh, two crystal of aluminum silicon are growing uh, adjacent to the silicon particle. So aluminum has like thermal conductivity of aluminum is high, of aluminum is around 205 watt per meter Kelvin, and for silicon it is 83 watt per meter Kelvin. So as the thermal conductivity of aluminum is higher than silicon, so it will dissipate more heat and will grow faster than the silicon particle. So as the aluminum grow, so this will stop the growth of silicon particles. Means this will be complete aluminum here, and the silicon particle growth will stop here. And also the latent heat of fusion, is for aluminum is 396 joule per gram, and for silicon it is 1411 joule per gram. So the latent heat of fusion for aluminum is less, so it will solidify uh, faster than the silicon. So both the thermal conductivity and latent heat of fusion help in aluminum solidification faster. So the silicon atom growth stops in the at the small sizes. So this is the second method to improve the morphology of silicon particles. Okay. So next question. Yes. Huh? That will be MCQs or a small numerical based question. Yeah. So I will discuss the MCQ questions also, but for the clear for understanding the concepts, I prepared these questions. Okay. Hmm. So the fourth question is, what is the significance of the second digit in the four-digit designation system? Sorry. For wrought aluminum alloys. So we represent the aluminum alloy like this 1XX, 2XX. So the first digit represents the major alloying element, and other three digits represent different for different conditions. So the second digit we have asked. So second digit represents the some alloy variation in uh, specific alloy composition. Means other than major alloying element, what is the modification we have done on this uh, a specific composition to the of an aluminum alloy? Like if we say 2214, so this second digit represents different meaning. Like if it is 0, it represents the impurity level uh, as other alloying element. And if it is 1 to 9, then it represents emphasized control to achieve certain properties. Okay, so emphasize control. Sorry, my writing is bad. Control on specific properties. So it means other than the major alloying element, some impurities always will be there in any alloy if we make. So to control specific properties, we can modify the those impurity in that alloy. So the 1 to 9 represent the different type of modification done to the composition to achieve the some specific type of properties. Like if we want higher ductility, so we can modify, we can reduce the elements which increases the uh, brittleness in the aluminum alloy, and to to inhibit the some formation of the uh, compounds which lead to the catastrophic failure during the service. So the 1 to 9 represents the control on emphasize to on the composition to control specific properties. So second digit represents variation in specific alloy. Okay. So next question will proceed. Which alloying element is primarily responsible for the strength in 2000, 3000, and 5000 series cast aluminum alloys? Okay. So can you tell me which major alloying element these three series have in casting alloys? Uh, yeah. So one. Okay, I will write it here. So one represents the pure aluminum. Okay. Second is aluminum copper. 3000 is aluminum manganese. 4000 is aluminum silicon. 5000 is aluminum magnesium. 6000 is aluminum magnesium silicon. 7000 is aluminum zinc. And 8000 is aluminum lithium. Okay. So these are the in the standard uh, form of the aluminum alloys, but they for casting we uh, we uh, we have a little variation. Like 2000 is the aluminum copper only, but 3000 is aluminum, magnesium, and silicon. Because in this 3000 is aluminum manganese, but aluminum manganese is very soft alloy, and it so generally we don't use casting for this. So in 3000 series for casting alloy, we use yeah, three digits. So this we can write it as 200.0. So dot is used in the week one lecture. The professor told that this only three digits are there. So zero represents the casting and one represents the ingot. Yes. So here we write zero for the casting. So it is dot zero. Okay. So the 3000 series, so 300.0 is the aluminum magnesium silicon, and 5000 is aluminum magnesium, yeah, aluminum magnesium. So in this, yeah, so the primary alloying element in this is the copper. In this, we have magnesium silicon, and for the 5000, 500 is or 5000, we can say also. So aluminum magnesium is the major alloying element. Which so these alloying elements form some type of precipitates if we do aging to these alloys after casting. So these like a aluminum copper will form Al2 Al2Cu intermediate precipitate. This form Mg2Si, and this form some type of complex intermetallic compound. So I don't remember for this, but for these two precipitate form to increase the strength of the this 2000 and 3000 alloy. So the major alloying element is for these series are copper, magnesium, silicon, and magnesium. Okay. So we'll proceed to next question. So why does adding solute atoms to a pure metal lattice typically increase the alloy's strength? So we know that the pure metal is very soft, and as we add some other alloying element, so it increases the strength of the metals. That's why we call metal and alloys. So metal are the pure, and they have very small uh, means strength is very low, and but the ductility is very good. So if we want to improve the strength, we add some type of solute atoms, means the primary metal. So other than the primary metal, so the solute atoms substitute some primary atom and form some type of substitutional and interstitial solid solution. Means are of two types: substitutional and solid interstitial. So substitutional is means the parent atom subs substitutes by the uh, added means the other metal atom. Parent atom is replaced by other atom. But in interstitial, the pure metal lattice will be is same as previous, but the spaces between the parent metal lattice, these interstitial atoms sits there. Means if this is the aluminum matrix, or these are the aluminum atoms. So at this space in between the four atoms, the interstitial atom sits here. So that's why it's called interstitial. So this site is interstitial site. So these interstitial site atoms are generally very small in radius. Like so yeah. So if the difference between the radius is very small or very large, means so the because of the large difference in radius, they sits in the interstitial. So some or we can add some type of uh, inorganic sorry non-metals also, like carbon, nitrogen, oxygen. So these atoms are smaller than the this metal atom, aluminum, copper, magnesium. So these atoms are very smaller than the aluminum, copper, magnesium atoms. So these sits in at the interstitial sites. So by forming the substitutional interstitial solid solution, they create some type of strain fields in the pure metal lattice. And because of the creation of that stress field, the motion of the dislocation will be uh, uh, harder as compared to the previous condition where no impurity or uh, substitutional atom are there. So because of the motion of the dislocation get hindered from the formation of these solid solution, the strength will be high. So this create some type of stress field, and because of this, the dislocation motion will be difficult. It's difficult. So that's why the strength increases when we add solute atoms. And it depends on the concentration of the impure means the substitutional or interstitial atoms also. Like if you make a stress strain diagram, sigma versus epsilon. So this is the curve for the pure aluminum. And if we add C1 concentration, so the strength will go up. And if we increase this concentration to C2, then the strength will increase more. So this is for C1 and this is for C2. Okay. You can ask if you have any doubt, or we can proceed to the next question. Okay. So next question is, what is the fundamental difference in how substitutional and interstitial solute atoms interact with dislocation types? Yeah, so the interaction between the solute atoms and solvent atoms are of four or five types. First is the elastic interaction. Second is modulus interaction. Three is the stacking fault interaction. Fourth is electrical interaction. Yeah. So four type of interaction between the substitutional and interstitial solute atoms with dislocation. Sorry, what is the fundamental difference in house? Just sorry, this is not. Yeah, so substitutional and interstitial solute atoms with dislocation types. Yeah. So substitution atoms means displaces the solvent atom. So this is the dislocation structure. Uh, So this is the extra half plane, or I will denote with this. This is the extra half plane. So this we call the edge dislocation because the displacement is of this type, means from one plane to this side, and this is the slip plane where the dislocation is moving. Means this extra half plane is moving in this direction. So the substitutional atom, uh, so in uh, can be of two types. Means if the radius of the substitutional atom, yeah. So first we will talk about the uh, stress field in the dislocation. So we can see that the atoms are more in the half above half plane, and the atoms are less in the bottom plane. So atoms, because of the high density of atoms, they are squeezed together. So because of the squeezing, compressive stress field generate here. And in the bottom is atoms are free and not compressed and as compared to this, so there will be tensile stress field at the bottom of slip plane. So the substitutional atom, if it is large, so in so where it will go means in the above plane the atoms are already squeezed, and if we want to add the substitutional atom here, it will be very means means that will be very difficult to fit the substitutional atom here if it is large, because it will create imbalance between these two fields. So if we want to reduce this compressive stress field in the above plane, so we have to add small substitutional atom, or and if it is large, so it will go in the below plane, bottom plane. So the large substitutional atom go at the bottom of the dislocation plane, and the small substitutional atom go in the above plane at arrangement atoms to balance the stress field of the dislocation. So here the small substitutional atom, and here it will be large substitutional atom, and the interstitial at solute atom, which are already very small and smaller than the substitutional also. So these this will sit at the bottom of the at the very near to the this dislocation code, means the this at this point, this is the dislocation core, means at the center of the dislocation field. So the interstitial atom sits at the core. So substitutional atom, so we know that there are two types of dislocation, edge dislocation and screw dislocation. Edge and screw. So interstitial atom can interact with both edge and screw type dislocation, because uh, uh, it can, because the dislocation core will be for both edge and screw. So interstitial atom can uh, sorry can interact with the edge and screw dislocation, but the substitutional atom uh, um, interact with most of the uh, sh- this edge dislocation. Means it can interact with sorry, with screw dislocation also, but the major Means most of the events we see for the substitutional atom interaction with the edge dislocation because of this large radius and comparable radius with the solvent atom. So it generally uh, interact with the edge dislocation. It is means a little confusing, but you will understand by time. Okay. So next question is how does the yes. Okay. Okay, yeah, you can means you can leave the meeting, but I have to complete it up to 7:30. So it's 15 minutes. Mhm. Or you can see the recording later also. It will be uploaded on the portal. Okay, so next question is how does the difference in elastic modulus between the parent metal and alloying element contribute to strengthening? So yes, so the interaction between solvent and solute atoms is of four types, means like elastic, then modulus interaction, uh, next is the stacking fault, and fourth is the electrical interaction. Okay, so from these four, modulus interaction means if the solvent and solute atoms are have different modulus, so the position where the solute atom sits, it locally changes the modulus of the uh, lattice, solvent lattice. So locally, it locally changes the modulus. So because of this local change in modulus, shear modulus also decreases. So this decrease in shear modulus, the the log so sorry, this decrease in shear modulus create some stress field or internal stresses, we can say stress internal stresses are generated, and that internal stress field uh, interact with the dislocation and impede their motion. So because of the change in modulus locally, the strength will be higher for this elastic modulus to play. So this means in the shear modulus change creates some type of stress field in the solvent lattice. Next question is in the context of stacking fault interaction, why does the segregation of solute atoms to the stacking fault make dislocation movement more difficult? So in stacking fault, what we see like this is the dislocation line and it dissociates into two dislocation lines by changing the orientation of the planes. Like first is the ABCBC stacking, So if we take out the C plane, so the stacking will be A B C C A B C. So because of this change in stacking, this dislocation line dissociates into two partial dislocation, and the solute atoms uh, get clustered at this area between these two dislocation partial. So because of this clustering of the particle in the stacking fault area, they uh, they oppose the further addition of these two partial into one. So that will be that reduces the energy of stacking fault. And we know that energy of the stacking fault uh, varies with inverse proportional to means this distance. So because the change in energy means the energy will be less, so the motion of this dislocation partial will be difficult when these cluster of particles will be present in between the two dislocation partial. So that's why the dislocation motion get hindered because of the this clustering of atoms in between the two partials. So next question is, how do valency differences between solute and parent atoms lead to electrical interaction that pin dislocations? So the valency difference between, means if we have two atoms A and B, so valency difference will impact the uh, means attraction and attraction and repulsion forces between two different atoms. Like if the bonding between A and B is equal to the bonding between AA and BB, so there will be random arrangement. But the AB interaction is greater than AA or BB, then this will lead to short range order. And if AB interaction is less than AA and BB bonding, then this will create clustering. So these three types of arrangement between these two atoms will changes the uh, energy of the lattice, and because of the lattice energy is changing, that will so because of the change in lattice energy, the dislocation motion will be impeded because of this uh, clustering, short range order, or random arrangement of these two atoms. So 11th question is, what are the key differences between short range ordering and clustering in a solid solution? Yeah, so difference is this, the means for the short range, AB interaction should be higher than the AA for short range ordering, and for clustering, AB interaction should be less than AA interaction. Then the clustering will be achieved. means the means the favorable condition for the short range order is the bonding between AB should be more favorable, and for the bonding between two different atoms is not favorable for the clustering. Means if it is less, A and B will not make a bond, then that will lead to clustering of A and BB. Okay. Then next question is, how does the movement of a dislocation through a region of long range order lead to the formation of an antiphase boundary? So the long range order form when the substitutional atom and solvent atom have almost similar type of properties, like elastic modulus is same, radius is same, modulus, radius is same, valence is same, then this long range order form. So we can make a matrix for long range. So this is the A atom, this is B, and we have one by one arrangement. So this is the arrangement for a long range order. So when the above plane displaces from its position, so the similar type of atoms will come in contact, like in, so this is the first condition. In the second condition, same type of atoms will come to next to each other. Yes. Okay, so this will create some type of boundary, which is called as the antiphase boundary. Because in the first condition, the one phase we have, but as the above plane moves, it will create two different types of arrangement. Because below this plane, we have this arrangement, and above this also we have this. Okay, so this will the displacement of this above plane will create some type of boundary which differentiate between two crystal crystal, or we can say two types which make two type of crystals. So this boundary is called as the antiphase boundary. Means two phases are created from one phase. So movement of a dislocation. So this plane movement is through the dislocation only, because means from uh, some fireplace dislocation plane is moving in this direction. So that will create this antiphase boundary. Next question is, why does the stress required to move a dislocation increase when it encounters an antiphase boundary? So as the dislocation from any other plane wants to move from this boundary, so the atomic arrangement is different uh, uh, far from this boundary. Means if we want to move from this place in this place, so the atomic arrangement is different. So because of that atomic difference in atomic arrangement, dislocation motion is hindered. So because of this difficulty in dislocation motion, the stress required to move from antiphase boundary increases. Means we have to apply more stress, then only this dislocation move from this phase boundary. Next question is, what is the solute atmosphere in the context of dislocation mobility and how does it form? So we know that if AB interaction is not favorable, then cluster of atom forms. And so because of this cluster formation, the cluster will go to the dislocation core and sits there. So because of the cluster formation in the dislocation core, it uh, it may I mean the dislocation motion will be difficult because of this cluster atom at the dislocation core. So that is called as the solute atmosphere around the dislocation. So this cluster of atom do not want to move the dislocation if we apply any stress. So if we want to deform our material, uh, so we have to apply more stress to break the cluster of atoms, apply more stress to break this cluster and to move the dislocation further. So this solid atom, solid atmosphere, uh, first depend. So the motion of this dislocation with the solid atmosphere depend on uh, two two. One is the velocity and second is the temperature. Means the two variables define the dislocation motion in case of solute atmosphere form around the uh, dislocation core. So velocity and temperature are the two variables to change the behavior of the cluster of atoms at the dislocation core. So if we how does an so that we'll address in the next question. So how does an increase in temperature affect the relationship between dislocation velocity and drag stress? So if temperature is high, So diffusion of atoms increase. So because of this increase in diffusion of atoms, they will tend to sit at dislocation core at faster rates. So the velocity of dislocation will be reduced, and drag stress to move the dislocation increases. Means we have to apply more stress if temperature is high. So because these atoms will move faster and sits at the dislocation core at faster rates. Next question is, what is the primary role of solute atoms in the development of yield point phenomena within a material? So yield point phenomena is that means change in yield point with time or with deformation. And time. Like if we apply stress, this is A, B, C, and if we unload the material, our sample at this position, and if we keep the material for some hours, then and reload it, so this the curve for that material will be of this shape. Means this is the upper yield point and this is the lower yield point. So the yield point will not appear for when we unload, rest it for some time, some hours, and then again reload. So this uh, yield point occurrence will not be observed with rest of the some hours. But if we put our material for a large gap, like for some months, if we keep our the deformed sample for a month, and if we again reload it, so this will appear. Now I will change. So with if we keep our sample for a month, then the this yield point will again reappear. Okay, so what is the primary role of solute atom in this behavior? Like if we deform the material and keep it for some hours and again reload it, so the diffusion solute atoms will not have won't have time to uh, go again at the dislocation core and impede the dislocation motion. So the yield point will not appear. But if we keep our sample for months, so the month means that time duration we increased. So with time at room temperature only, these solid atoms again go to the dislocation core and lock them to move further. So that's why the now this yield point will reappear when we reload it after months. So this changing in yield behavior of any material or aluminum alloy is because of the diffusion of solute atoms and the dislocation core interaction. Okay. So next question is, how does the upper yield point differ from the lower yield point in the context of dislocation movement? So upper yield upper yield point is this and lower yield point is this point. So at this upper yield point means we have solute atoms uh, at the dislocation cores. So we have to apply first higher amount of stress to unlock the dislocation from their core. So as the dislocation get free, the motion or dislocation will be easier and the deformation will proceed easily. So that's why the stress reduces after the upper yield point. Upper yield point, this is lower yield point. So because the dislocation now gets free, this stress reduces up to a certain point. Then after some time, this stress again increasing because of the interaction between different dislocation. So dislocation density increases with time and deformation. So that's why the stress is increasing again. So the difference between upper yield point and lower yield point is that the dislocation gets free with applying of high amount of stress, and these free dislocation move easily to deform the material. So that's why stress reduces to low yield point. The next question is, why does a material exhibit different stress strain behavior when reloaded after aging for only a few hours versus a few months? So I discussed in the that 16th question, like the solute atoms will again uh, lock the dislocation core, and because of the locking of dislocation, the yield point means the yield point phenomena. This is the yield point phenomena again reappear after months, but for shorter times, the solute atoms could not easily go to the dislocation core and hinder them. So that's why the yield point will not appear for some hour age, aging. So this the rest of this material after deformation we call it as aging. So aging of few hours. Yeah, so aging of few hours. The solute atoms are not able to log the dislocation, but for a few months, the solute atoms diffuse to the dislocation core and lock it. That that's why yield point reappears. Okay. So next question is, how does temperature influence the rate of strain edging in metallic alloys according to the principle of diffusion? Yeah. So temperature we have the so uh, the velocity of this is the atoms. Sorry, drift. This is the drift velocity of atoms. So drift, the atoms get some type of drift velocity because of the stress field around the dislocation. Means some type of uh, equipotential lines form around the dislocation core. This is the dislocation core, and this type of the energy lines form at the dislocation. So at the circle which is very near to the dislocation core have higher energy, highest energy. And as we move away from the dislocation core, the energy decreases. So because of this energy difference, the energy gradient is present around the dislocation core. So because of this energy gradient, dislocation the some type of they create some type of force around the dislocation. So the force line will be of this red curves. So these are the flow lines. So solute atoms, as they come near this stress field, they will feel some force and move frequently around the dislocation because of this energy gradient. So because of this energy gradient, they get some drift velocity, and that depends on the d by kt into f. So F is the force created from this stress field. D is the diffusivity. K is Boltzmann constant. T is absolute temperature. And F is the force applied by stress field. So with the temperature, the strain aging. Uh, so as we apply the temperature, diffusivity will be high. So the drift velocity of atoms will be more, and that can impede the dislocation core easily. So with increase in temperature, the diffusion increases and strain aging will accelerate. Okay, so next question is, what is the significance of the quadral Bilbao theory in explaining the interaction between dislocation and solute atmosphere? So the quadral Bilbao theory means extend the this energy gradient concept further. So it tells us the accumulation of atoms to the dislocation is given by the some number of solute atoms that accumulate in a specific time dt. So it is a number of solute atoms according to the quadral Bilbao theory accumulated in time dt from a length is given as a d by kt by r square. R square is the distance from the dislocation core of atom. This is the dislocation core, and this is at point P. Atom is there. So this distance is r, and this is the theta. So if we integrate this number of this of equation, so number of solid atoms will be, so if we integrate it from r, this will be a d t by k t raised to power 1 by 3 from r to r infinity. So total, if we uh, take total accumulation from t to dt, is this will be a d by k t raised to power 2 by 3 dt by 1/3. So this term represents the area that supplied solute atoms between T and T plus dt. And here we will write 2 because of the both sides of flow lines. Means both sides of flow lines are accumulating solute atoms at the dislocation length. So we can write NT, which is number of segregated. Sorry for this. Okay, so number of solute atoms accumulated in time dt is given as AD by KT by R square. And by integrating it with R from R to infinity, we get this term as ADT by KT raised to power 1 by 3. Then total accumulation from T to dt will be given as 2 AD by KT raised to power 2 by 3 and dt by T raised to power 1 by 3rd. And 2 comes because from the both sides of flow lines. So NT, if we calculate, so NT is the number of segregated solute atoms on a unit length of dislocation is given as NT equals to alpha N naught AD by T. So AD small t by K capital T raised to power 2 by 3. So alpha is generally a constant and it is 3. So and naught is the initial number of solute atoms. solute atoms per volume. So from this, the fraction of solute segregated to the dislocation. So this is the total number, and the fraction of these solute atoms is given as Nt rho by N naught. So rho is the dislocation density. Okay. So next is the MCQ type question. What happens to solute atoms when there is an energy gradient near a dislocation as opposed to when there is no energy gradient? So they tend to move more frequently in the direction of decreasing interaction energy. So B option is correct. According to the theory, the rate of arrival of solute atoms to dislocation line varies with time according to which power law. So here we derived it 2 by 3. So T raised to power 2 by 3 is correct. Third is, why is the factor of 2 included in the solute accumulation expression during the derivation? So uh, because there are two types of solute atoms, no. Dislocation moves twice, no. Because there are flow lines on both sides of the dislocation. So C option is correct. So we'll discuss now the assignment questions. So first question is, which of the following designation is used to notify wrought aluminum alloy with copper as a major alloying element? So wrought aluminum alloy is given by four-digit designation. So 2000 is the correct answer. And B option. Next question is, what does the second digit in wrought alloy designation indicate? So it represents variation in specific color. C option is correct. Next question is, which of the following aluminum alloys are heat treatable? Heat treatable means we can increase strength with addition of with doing some heat treatment. So 2000 form precipitate, 6000 form precipitate, 7000 form so it is aluminum zinc, it is aluminum magnesium silicon, it is aluminum copper. So both three alloy system are heat treatable. Which of the following statements are correct in case of aluminum alloy designation as AA7XXX? So it contains zinc as a major alloying element. It is correct. It is a cast alloy which is fabricated in near-net shape products through casting route. This is correct. It doesn't form precipitate when subjected to heat treatment. No, it is heat treatable. It is a wrought alloy which is subjected to secondary processes for reshaping. No. So first, second option is correct. Next question is, when aluminum 7% silicon alloy cooled from 700 degrees Celsius to the room temperature, then its microstructure will contain following phases. So aluminum 7% silicon is hypoeutectic alloy. In the hypoeutectic alloy, first primary alpha aluminum form, then eutectic silicon form. So C option is correct. Eighth question is, the phase responsible for low ductility in hypereutectic aluminum silicon alloy is. So hypereutecticity in hypereutectic aluminum silicon alloy, the primary silicon particles form in large amount. So the primary silicon particles decreases the ductility because of their sharp edges, and the number of silicon particles are also high, so ductility will be low. So primary silicon particles are the correct answer. Which of the following statements are correct regarding modification of aluminum silicon alloy by addition of small amount of chemical modifiers? So chemical modifiers deactivate the TPRE mechanism, correct? It adsorbs on surface and prevent the attachment of silicon atoms to the crystal. Yes. It promotes grain refinement. No. It prevents the growth of silicon crystal by complete encasement of aluminum crystal. No. First and second option is correct. Next question is on cooling of aluminum silicon alloy with higher cooling rate during its solidification. So because of higher cooling rate, the silicon particle morphology will be uh, less detrimental, and that increases the ductility. So ductility of the alloy increases. Morphology of eutectic silicon changes from coarse needle to fine fibrous form. So B and C is correct. Next question is when aluminum 14% silicon alloy cooled from 700 degrees Celsius to the room temperature, then its microstructure will contain following phases. So aluminum 14% silicon is hypereutectic alloy in which primary alpha aluminum form, proeutectic silicon particles form, and eutectic silicon phase also form. So the fourth option is correct. Second is addition of a small amount of chemical modifiers in aluminum silicon alloy. It deactivates TPRE mechanism, prevents attachment of silicon atoms to the crystal, prevent growth. So B and C is correct. Third question is on cooling of aluminum silicon alloy with a lower cooling rate during its solidification. So the lower cooling rate will increases the silicon particle size, so ductility decreases. First is correct. Morphology of eutectic silicon changes from coarseness and no, this is not. Morphology of eutectic silicon will be of coarse needle types. So first and fourth option is correct. Fourth question is hypereutectic aluminum silicon alloy are known for their higher hardness. Hardness will be high. The silicon particle will improve the wear resistance. So higher wear resistance. So B and D is the correct answer. What do the last two digits in the Rot alloys designation indicate? So last two digit indicate purity level, like 1145. So it is 99.45% pure. Sixth question is in elastic interaction, the strain field associated with interstitial solute atoms will interact with both edge and screw dislocation. The option is correct. Seventh question, which of the following statements are correct about solid solution strengthening and aluminum alloys? First is substitutional solute atom larger than host atom imposes tensile stress field in the lattice. No. Larger atom will create compressive stress. So first is wrong. Second is interstitial solute atom larger than interstitial space imposes compressive stress field in the lattice. It is correct. Third is dislocation motion is hindered due to diffusion of solute atoms into the dislocation core. Third is also correct. So second and third is correct. Eighth question. Strengthening of aluminum alloys through electrical interaction is mainly due to local change. So electrical interaction generate because of the difference in valency. So valency difference between solute atoms and parent atoms. Second option is correct. Ninth question is stress required for dislocation to move through the antiphase boundary. In so stress is equal to energy of antiphase boundary by spacing, antiphase boundary spacing. So it increases with the decrease in APB spacing and with increases with decrease in APB. This is wrong. Increases with clustering of tendency of solute atoms. No. So only second option is correct. Increase with a decrease in APB spacing. 10th question is drag stress or interaction stress between solute atmosphere and moving dislocations will increase when drag stress increases when dislocation velocity increases. No, drag stress, interaction stress between solute atoms and moving dislocation. When the dislocation velocity decrease, the solute atoms can easily log the dislocation, so the drag force will increase to move the dislocation. So dislocation velocity decreases and no temperature should increase. With strain rate increase, the dislocation will freely move without any solid atmosphere interruption. So only D option is correct. Dislocation velocity decreases. So this is all for today. We'll discuss the week 3 lecture in the next week. Okay, then thank you.